Okay, guys, I want to take a minute here to just show you the lab that you would have done if you had a computer that was Java equipped. I'm using a PhET simulation that is not HTML5, it's Java only. So if you can do this at home, that'd be great, but I know that some of you don't have a computer that does that. Miracle that my computer actually does it and actually works. So let me show you really quick how this is going to work. What I've done is I loaded a packet online this morning for this is a lab we would have done. So we'll do these problems either on paper or I'll show you simulations, or you can try it as a simulation yourself. But you should understand what's going to happen. And remember, we're going to look at two different situations. We're going to look at immediately after we close the switch, or literally close the switch a trillionth of a second later. What are the meters going to read? What's going to happen? And then we're going to look at it a long time later. The APE does not require you to understand what the circuit exactly will read in between, but we know the charging and discharging curves that we talked about before, and this lab is going to show you that. But they typically ask you about what happens immediately after you close the switch and a long time after you close the switch. So we'll look at both those situations. So in your packet, we have three circuits I've designed, and we're going to test these and see if they make sense. So the first circuit on page 1, you'll see there's a 9-volt battery, and I've set this to 9 volts. You can right-click on these things and change the voltage, and it should be set to 9, and it is. Then above that, we go up, and there's an ammeter connected in series. So we're going to pay attention to that during the process. We also have a switch, obviously, to open and close. Then we've connected it to a capacitor. The capacitor should be a 0.2 farad, and I've set that to 0.2. And then down here we have a resistor, and resistors we use to dissipate the energy in the capacitor. So, and let me look at that value. It's also the RC value is also going to set the time constant, how quickly or how slowly it charges and discharges. So this is really looking at the charging curve. Now, at the top of your lab sheet, you'll see this RC constant. And we did this in the other lab. We didn't actually do the lab, but I showed you what you would have done. I built the circuit and showed you. In that lab, I picked a particular R value and a particular C value and got a RC constant. We saw how long it took to charge and discharge that capacitor circuit. In this case, if I take the R times the C, that equals 10. And the tradition is that if you wait 5 RCs, if you wait 5 tau or 5 timing constants, then that will pretty much put the capacitor into what we call equilibrium. It will be done doing what it's going to do. So 50 seconds is essentially the same as 1,000 seconds. I think it's 99.3% of the process is done. So in this case, I'm going to set this clock up here. I'm going to reset and stop and then start. So this is, because I have this thing on pause right now, it's on pause mode. It doesn't matter if I close the switch or open the switch. It can't run. So I have the switch closed. I have the clock reset. It's ready to go. As soon as I click this button, it's going to start, the circuit's going to start operating. Now I'm going to click it and immediately click it again. So I'm going to essentially be closing the switch and opening the switch, but I'm doing it by controlling it down here. That will allow me to see what the meter readings are immediately after closing the switch, and you should be able to predict what's going to happen based upon our conversation we had in class. I'm going to put the voltmeter across the capacitor. And for some reason, it's reading negatives. It's treating as if these terminals are backwards, but I'm not sure why, but it doesn't matter. So we may get negative values versus positive values for voltage, but it won't matter. So I'm going to click on this, open it, close it, or close it, then open it immediately. So ready, set, boom, boom. Now, when I did that, and again, I was probably not as fast as I could have been. I could have been click, click. You'll start to see the capacitor has started to charge. There's some charge built up on the upper plate, positive, and some negatives being driven off the battery to the bottom terminal, some electrons leaving, and leaving the top terminal, the top plate positive. You'll notice there is a little bit of charge built up, and therefore there's a little bit of voltage across the capacitor. Remember, this is 9 volts. It's going to try to do it until this becomes 9 volts. So we're definitely early on in the process of that charging curve. You'll also notice that the current has spiked. And when I run this for a long time, I want you to sort of pay attention on both these back and forth. You're going to see the current is going to go down pretty rapidly, and the voltage is going to go up pretty rapidly, at least initially. And then as this becomes closer and closer to 9, this process will slow down, and this will also slow down. So it'll go to 0, and this will get closer to 9. You can tell I ran this for less than half a second. So in your lab, you can actually write down these values in that first page. Immediately after closing, you can write down this value for the current for the ammeter reading, for the current in the capacitor branch. It's the same thing. The change in voltage across the capacitor is essentially zero. It's 0.317. The voltage drop across the resistor must be the rest. So this better be 8 point something, and it is. It's 8.682 because, again, the battery drives the voltage up 9 volts. There's going to be a drop across the capacitor and a drop across the resistor, and the two drops better add up to the rise, and they do. So again, I'll bring this back over here. And again, I'm not sure why it's showing the voltage as being reversed. I did run the simulation a minute ago. Maybe that has something to do with it. But anyway, now I'm going to run this circuit. I'm going to run it for a long time. I'm going to run it for 50 seconds. So pay attention to the ammeter. It's dropping, and the voltage is rising very, very rapidly. There's a lot of change taking place. The voltage is building. The ammeter is dropping. But you'll notice that as it gets closer to 9 volts, it's going to slow down. It's slowly rolling over. So 6.6, 6.7, 6.8, 6.9, 7. The ammeter is dropping down to 0.03, 0.02, hopefully soon. Now look at this. It's going to climb, but it's going to slow down. 8, 8.1, 8.2, 8.3, 4, 8.5. And as you get closer and closer, we've only gone halfway through the cycle here. We're going for 50 seconds. You'll notice it's going to climb, but it's climbing much more slowly now. 8.8, 8.9. So you get the idea. As we get closer and closer to that 50 seconds, and I'll stop this at 50. 49, 50. So it's pretty close. We're at 50 seconds. We're at 5 tau or 5 RC. The current is essentially gone to 0, or almost 0, and the voltage is almost equal to the voltage of the battery. And of course, if I check the voltage across the resistor, this should be essentially 0, showing you, again, there's no current, therefore there's no voltage drop. So there's a tiny bit left. So again, that's the basic idea. This is a basic charging of the capacitor. We could discharge this by hooking up another light bulb over here like we talked about before. But this was the lab you were going to do, and it's kind of nice to be able to check. We can't actually build these circuits in class. You can, but it's hard to do. It's hard to measure the values. So FET works pretty well. But again, you should be able to go through this packet and understand what each of these circuits are going to do, both at the immediately after closing and after a long time. And if possible, I'd love it if you guys could build the circuits and actually test. Now, what I'm going to do in the subsequent, the next version, I'm going to replace this by putting a couple different resistors in here. That's going to raise the R, which is going to raise the RC, and you'll see it even charges and discharges even slower. So remember, the RC controls the charging and discharging rate. So that's all I wanted you to see is how we could build these circuits in the lab or in the simulation and control what's going to happen. Okay, we'll try to take a look at the rest of the packet. Okay, let me knock this off.